Good morning, good afternoon, good evening, good wherever you are, and welcome to another SNEER webcast. This one is from the Networking Storage Forum, and today we're continuing our series about security. Our storage networking security series has been very popular so far, and we've added to it with this session on applied cryptography. So now you know where you are. I'm going to tell you a little about the interface very quickly in case you haven't attended the Bright Talk before. The interface is relatively straightforward for you. You'll see on somewhere on the screen, you'll see you're able to make the screen full size should you need to. Some of the detail in the slides might be lost if you're viewing this in a relatively small window. So if you need to make it full screen, you can do so. Secondly, there are a number of buttons that you can press to get extra information. The first one is attachments and links. We've got the presentation in a PDF format for you to download, and a couple of other links as well, one of which, if I can get my mouse to behave itself, is an entry to the blog for this, where we'll be posting up answers to any questions we get during this session. And secondly, to SNEER's blockchain storage technical work group, where we're doing technical work on blockchain that'll be covered at the back end of this presentation. The other thing to note is that you have the ability to ask us questions during the session. Please feel free to do so, and I'll make sure that they are either asked and answered during this session, or if we can't get to them, that they're answered on the blog. The second thing is that you can rate us as you leave the presentation today. You can score us on from 1, I'd rather be doing something else, all the way up to 5, which is more. We really like this. That's the highest rating you can get. So score us on the way out from a 1 to a 5. So without further ado, let me start by introducing our speakers today. I'm Alex McDonald. I'm the Vice Chair of the SNEER Networking Storage Forum, and I work for NetApp. And I'm joined today by John Kim, who's the Chair of the NSF and works for NVIDIA. Good morning, John. How are you?
Hello, Alex. Doing well, thank you.
Good, good. That's John. We're also joined by Eric, who has more letters after his name than you can shake a stick at. Eric Hibbard is, I think, you're working for yourself now, aren't you, Eric? But Eric
That's right.
does an awful lot with SNEER security, technical work group, INSITs, a variety of tech. We've got an expert here in terms of some of the technology that's being covered today. And lastly, we're also joined by Olga, whose surname I've been practicing, and I'm going to give it a go. Okanina. Is that right, Olga?
Yes, you did it.
Hooray! Got it right. Practice makes perfect. And she's chair of the blockchain storage twig that's in the link on the right-hand side, and also works for a company called ActionSpot. So those are our speakers today, John, Eric, and Olga. Before we start, just let me do a little bit of the legal bit. Basically, this presentation doesn't come with any particular warranties, and if whatever you do with this presentation causes whatever you're doing it to break into 2 bits, both of those bits are yours, not ours. And lastly, we would like you to at least understand there are some copyright issues with these things, that SNEER owns the copyright to this presentation, and if you could act appropriately when using it. That's the legal piece over. None of us is a lawyer here, so if you need to use it, do so with that in mind. SNEER itself, the Storage Networking Industry Association, has around about 185 organizations that are members. It's a very large organization in that respect, and it represents most of the big names and the small names in the storage networking industry. We've got about 2,000 active contributing members who partake in technical work groups and forums like this and generate both technical standards and also educational material, and about 50,000 end users and storage professionals worldwide with whom we communicate on a regular basis. That's you. If you want to learn more, there's a website link there, sneer.org/technical, and we also have a Twitter handle @SNEER that you can follow. And I'll give you more information on links to various parts that are relevant to this presentation as we come to the end of it. So what does the Networking Storage Forum do? Well, we cover a variety of technologies: Ethernet, iSCSI, NVMe over fabrics, a wide range of the kind of things you would expect to happen when you're looking at storage. We also cover, as you're seeing in this presentation, pieces that are ancillary to storage as well, like, for instance, that important aspect of security, which is becoming increasingly important over the years as people get more savvy about the kind of information that is being held. There are more attacks on that information. There are more requirements that are legal in nature that require us to look after that data and information that we're collecting. So that is an additional area of interest for the Networking Storage Forum, and hopefully for you as well. So without further ado, the agenda today is authenticating users, encrypting data, hashing, and a bit about blockchain. So I'm going to let John Kim start us through this presentation today. John, over to you.
Thank you very much, Alex. Hi, this is John Kim, and I'm going to talk about authenticating users and encrypting data, and a little bit about asymmetric versus symmetric encryption as it applies to both of those. So first, let's cover authenticating users. So the question arises when you're on the internet or logging into a server or even within a data center is, how do you know that someone or something is who he or she claims to be? How do you know a server actually belongs to the company, the website that you're trying to visit, or that a user who wants to connect to a server or application is in fact that user and not an impersonator or impersonating website or a man in the middle trying to steal someone's data? So one answer is certificates, and certificates can be used by servers or users, but they're most often used just by the servers, typically web servers or web applications. And they verify the authenticity of a server or a website so that people know that it is in fact, if you go to the NewYorkTimes.com or Yahoo.com or Google.com, it really is the site that you're trying to visit. And these certificates rely on a trusted certificate authority. These are people who issue certificates and are generally trusted and known to be who they are, and that the certificates they issue can be trusted to verify who the certificate owners are. So if I am a certificate authority such as Symantec and I issue a certificate that says the Microsoft.com website is really Microsoft.com, users can get that certificate and know with a pretty good level of confidence that they are in fact visiting Microsoft.com and not something that just looks like it. For verifying user identity, most often you have user credentials. The most common is a username and password, but you can also use biometrics such as a fingerprint or a facial scan, and you can use two-factor authentication, which typically relies on sending information to an email account or a phone or other device that's assumed to be owned by that user, and therefore verifies their identity. So authentication of users or websites often starts with asymmetric encryption, and I'll talk more about that in a second. But asymmetric encryption is often used to first establish the set of establish identity, or to establish a set of keys that are then used for symmetric encryption if you're encrypting data transfers or data at rest. Other ways to authenticate users include using hashes or blockchain, and that can be used to authenticate users or the data. And Eric and Olga will talk more about those two methods in their sections. So before I dive into more about authenticating users and encrypting data, I want to talk a little bit about keys, and this was covered in more detail in our encryption webcast on key management, which there'll be a link to that at the end of this webcast. So with keys, or encryption keys, usually you have symmetric and asymmetric. In symmetric, you encrypt and decrypt the data with the same key. So the server or application or the user holds the key, and if there are other people or other applications that need to access that encrypted data, they're also given the same keys. So you share the keys with whichever users, servers, or applications need to encrypt and decrypt the data. So this method is usually for a limited audience where you have a small number of users, perhaps just one user or one server or one storage controller that needs to encrypt and decrypt the data. So you encrypt it with and the person or device that's doing the encryption and decryption holds the key, though it may work with a key management server or key management application to do so or to update the keys in the future. With asymmetric encryption, there is a pair of keys. One is public and one is private. Typically, only one person or device holds the private key, but anyone can have or does have the public key. And asymmetric encryption typically uses something called a trapdoor or one-way type encryption, meaning that if you're encrypting with the public key, it's very easy to encrypt, but it's almost impossible to decrypt unless you have the private key. And likewise, if you encrypt with the private key, then anyone can decrypt it with the public key, but it's almost impossible, or should be practically impossible, for anyone to make the same kind of encryption unless you have the private key. So the typical use cases for asymmetric encryption are if you want to encrypt data for a one-way data encryption, like sending, for example, a key for setting up encrypted data transfer, or sending a certificate, which everyone can, if you want to send the data that you can encrypt, but only the proper recipient can decrypt, you use asymmetric where you encrypt with a public key. This is the first example shown here. And then only the people holding the private key can decrypt it. So anyone can encrypt, and then only the private key holders, which is usually just one server or one group, can decrypt the data. On the other hand, if you want to do some authentication like digital signing, to sign a certificate, to verify the identity of a web server, then you encrypt it with the private key, and anybody can decrypt it with a public key. So that's going the other way. Anyone can decrypt it, but only the person with the private key can encrypt it. And if you're able to decrypt it with a public key, that verifies that it was encrypted or came from the person holding the private key. So let's talk about how this applies if I want to authenticate, perhaps authenticate a user and do data encryption on the wire. And we'll have a slide with more information about data encryption on the wire in just a minute. But a typical session, which might use authentication and encryption, may start out where a website gets a certificate from a certificate authority. So the certificate authority does some verification that the website is in fact who they say they are, and then issues a certificate that's encrypted with the certificate authority's private key. And they issue a private key and a public key to the website. The website holds on to the private key and keeps it secret, but makes the public key available to anybody. So when a user or a web browser contacts the website and says, I want a secure browsing session, the website then sends a certificate, which is signed with a private key, and the user or the web browser uses the public key, which everyone can get, to verify that the certificate is valid, that it was encrypted with a private key owned by the website, and it links to or it includes a certificate from a known certificate authority. So now the user has verified that the website is in fact the website they want to get to and is not an imposter. The user then sends either a proposed shared secret or the tools to make a shared secret, depending on the type of encryption, and they encrypt that with the public key from the website. So sending it this way, anyone can make that encryption, but only the website can decrypt it with the private key that it holds. So now this shared secret, or this information which we use to generate a shared secret, is held by the user because it created it, and then held by the website because only the website can decrypt it with its private key. So now that both the user and the website have the same shared secret, they generate a symmetric encryption key, and they use that to start their encrypted data session. Where in this case, you can see that they both have the black key. They're using the same key on each end, on both ends, for symmetric encryption for actually transferring the data. So this is a typical example where you verify the identity and then you send the information for making the temporary shared key using asymmetric encryption, and then you use symmetric encryption to actually encrypt the data that goes back and forth, for example, using TLS or SSL. So I've already mentioned it in the example, which I needed to talk about the asymmetric versus symmetric encryption, but a little more about encrypting data. So encrypting data protects it from unauthorized access. Usually there are a couple of ways. One is you block users from getting to the data they're not supposed to have, or the servers, but in case they are able to get to it or they break through that first level of security, if you encrypt it, then makes it hard or impossible for the people to use or read the data that they might have accessed or stolen. Using encryption can help with regulatory compliance when you have rules that require certain types of security or privacy. And there are many regulations. We have a separate webcast. We did a separate webcast on that as well. So encrypting data can be done with data at rest or data on the wire or with both. And again, it can use symmetric or asymmetric keys depending on the use case, though in the end, the actual data encryption is usually done with symmetric keys, and asymmetric keys are usually used just to set up the encryption or set up the, to help create the symmetric keys that are used for that. So an example of data at rest, here we have an application running on a client or a server, and then we have a storage controller, which has some storage media, could be hard drives or flash drives or some other kind of persistent memory. And then we may have a backup destination, and the backup could be a backup server, a tape library, or a cloud service, which is in fact probably more and more common these days. So the encryption of data at rest protects against the theft or reuse of the storage media. So it protects in case somebody steals the server or the hard drive or the flash drives, or if someone bypasses network security or goes or gets through it and manages to get directly onto the media, then encryption can help prevent unauthorized use or access of that data. Encryption of data at rest usually does not protect the data in transit, though there are exceptions to that. So if I encrypt the data at the application level, then even though I've encrypted it before it's transmitted, effectively it is encrypted on the wire because it was encrypted by the application before it's transmitted to the storage and then possibly transmitted to the backup. However, if I encrypt the data at the storage controller, then it's not encrypted on the wire, except as it goes to the storage media. And then usually the storage controller will encrypt it as it goes to the storage media and then decrypt it as it reads the data back and transmits it back to a client or a user. The encryption at the storage could also be done by the storage media if you have like a self-encrypting drive. And in that case, the storage controller passes the data in the clear to the media, and the media encrypts it using a key or a set of keys. And then finally, the data that goes to the backup is often encrypted, and that encryption is usually separate or in addition to what's on the storage. So when the data passes from the storage controller to the backup device, if this data was encrypted by the storage controller or the storage media, it can pass the data either as encrypted or decrypted to the backup device. So obviously, if it's passed encrypted, then it's already encrypted, and the backup device may or may not need to encrypt it again. And if it's passed in the clear, then the backup device or backup service would have to do its own encryption to protect the data from unauthorized access or theft from the backup service or backup device. So again, we see that encryption of data at rest can be done in multiple places. If you do it earlier in the chain or upstream, so to speak, at the application or user level, then it's already encrypted as it gets downstream to the storage or the backup. And again, if you do it at the storage level or storage device controller or storage media, then it may or may not be encrypted when it goes to the backup, depending whether or not you decrypt it as you read it from the storage device into the backup. And then the backup devices or services can do their own encryption if they want. And a key is that the device or service doing the encryption is also doing the decryption, so it holds the key or keys for that. For encrypting data in motion, there we go. So in this case, this is for protecting the data while it's on the wire or on the network. So in this case, both devices at either end of the connection will encrypt and decrypt the data as it's moving or right before it goes to the network or right after it comes off the network. So this by itself does not protect the data while it's at rest, but again, many people will combine both. They'll encrypt data at rest and encrypt data in motion. So we see here that the client and the server are encrypting data on the wire using the black key, so it's symmetric. They use the same key on each side of that connection. And then the server and the storage could have their own encryption on the wire using the red key or the violet key. In this case, they're also doing symmetric encryption, but with a different key. And finally, the storage and the backup have the option to do symmetric encryption when they communicate using the gray key. So typically, each connection will have a different key, but will have the same key on both sides of that connection with symmetric encryption. Though again, the setting up that symmetric encryption key is often done with a process that uses asymmetric encryption. All right. Oh, and I forgot to mention that, sorry, my last bit is that this encryption can be done in software, or it can be accelerated with a special software library with special routines in the CPU, or by using a SmartNIC or an FPGA, typically on an FPGA card. So the encryption can be done purely in software or partly or entirely in hardware for faster results. All right, Alex, that's the end of my section on, and I'd like to now pass it back to you so we can get into Eric and hashing.
Thank you very much, John. So, Eric, the guy with all the letters after his name, take it away.
All right. Well, that's true. I am fond of the letter S. So I'm going to talk about a special piece of cryptography, in particular hashing, which is used quite extensively. And unlike encryption, which is another component of cryptography, where you are basically protecting information and being able to reverse it, hashing doesn't have that kind of characteristic. So just as some background on hashes, we're going to talk specifically about cryptographic hashes. There are other kinds of hashes, but these are focused on the cryptographic versions of these. Some basic concepts, you can take numerical input, any value, basically almost any size, run it through one of these functions or algorithms, and you get a compressed numerical value out the other side. So think of this as arbitrary length input, fixed length output. The fixed length is typically fairly small, as in you could have several gigabytes of input and maybe 128 bits coming out on the other side. A key component of this is that it should be computationally hard to reverse a hash function. In other words, if you have the hash value, in reality, you should not be able to reverse from that value what the contents of the original input. And as you probably guessed, if you've got multiple gigabytes of information, reversing that out of 128 bits is going to be quite difficult. A bigger problem, however, is a situation where you have two input streams that result in the same hash value. So that 128 bits in my example, if you have two sets of inputs that are different and you get the same hash value, that's known as a collision. And when you start seeing that, that's when you'll see the hash function essentially be retired, because there's now a problem, if you will. And there's a lot of people who are constantly sort of probing these hash functions to see if there are techniques they can use to come up with it. So why would this be important? Well, if you were to edit the file that contained your salary, and your salary is $10 an hour, and you edit it so that it's $100 an hour, if you were able to figure out how to change other attributes of that file so that they both had the same hash value, then somebody checking to see if the integrity is still in place would go, oh, it's fine, but you've now gotten a raise. And that's just an example of potential problem. Pictorially, this is a simplification. So this is the arbitrary length message in, the hash function, and then the output value. So sometimes it's easier to see just sort of picture. But really, under the covers, there's a little more going on than quite that. And this shows you a little bit more in that the input is being broken up into fixed length blocks that are then going through an algorithm, and you see basically a chaining kind of operation where there's a seed that's used to sort of start off the algorithm. You run a chunk of data through, and I'm oversimplifying here, but you run a block of data through the algorithm with that seed value. It produces essentially a value that's used as input along with the next block, and you repeat the process all the way through the end. And if you have a the last block is not quite a full block of data, then you actually add some padding. The significance of this is that, and this is how a single bit change in that input data will result in a different value of the hash value, is because there's this constant dependency of the previous data through this computation. Part of the other reason for showing you this is that these cryptographic hash functions are not computationally cheap to perform. There's a lot of calculations that are actually being performed here. And so when you invoke one of these, you should anticipate that it will have, an impact. And this plays back into, for example, when John was mentioning the use of TLS or SSL, there are hash calculations that are being performed, and this sort of contributes to the computational cost of, in some cases, just starting up the connections and whatnot. Okay, so here are a set of fairly popular hash functions. Hopefully you're not using message digest anymore because lots of collisions have been found, and MD5 was basically the last one that was being used. The scary part is for years and years, the default hash function for SSL and earlier versions of TLS was actually message digest, even after there were lots of collisions found. Later versions of TLS are no longer using that, but this is something to be aware of and not use. That takes us to the next set, which is the secure hash function. This is something that the US government has been heavily involved with, and you see that there are 3 different flavors: SHA-1, SHA-2, SHA-3. There have been collisions found for SHA-1, and you're already seeing guidance from NIST as part of the U.S. government to sort of move away from SHA-1 and move to SHA-2. SHA-3 is fairly new, and we're seeing organizations are beginning to use it on a regular basis. Now, as I mentioned earlier, there are fixed outputs for these hash values, and what you see here is, for example, SHA-1 is a 160-bit hash value, and the block size is 512 bits. Well, some of these others under SHA have, depending on which flavor you choose, different output sizes, and also potentially different block sizes that they're using to essentially work their way through your data. There's a couple others in here. There's RIPM 160 and its brethren, and that is one of the hashes that's used in Bitcoin, and Shibboleth is also used in some of the blockchain work. So these are functions that you probably hear about, and they are all cryptographic hash functions. Okay, so I'm going to talk a little bit about how some of these get used. And the first application is basically dealing with passwords. And so everybody knows or should know that passwords should be protected, and everybody's thinking that they should be encrypted. And in fact, in most cases, that's not actually what's happening. What's being stored in the password file is essentially a hashed version of the password, but it's not just the password, because if you know the function and you know the password, or you could guess the password, it would be easy to sort of rip through and reverse engineer what the passwords are. So there's a salt value or a seed that's not known, that's added to your input password, which then produces a unique hash value, and it's the hash value that's actually stored. And the process is when you submit your password to a system, the system will basically take the known seed and combine that, hash it, And then there's a comparison of what's in the password file. All right, so there's not actually a need to store the password on the server side. All right, so if the comparison works, then you're authenticated. If it doesn't, you are not authenticated. And of course, it's important to keep in mind, because you have to hand a clear text password to the system to do this. You never want to pass passwords in plain text form. So something like TLS or some sort of encryption on the communication path is absolutely necessary. Otherwise, you run the risk of having it intercepted. The next application to talk about is data integrity checks. And here, you're using the hash to determine whether anything has changed in the data. And this is back to, remember when I was describing how the algorithm works, a single bit change will result in a different hash value. So if you have a hash of a file, for example, and you transmit that file to someone as well as the hash value, they have the ability to check on the other side whether or not anything changed. Now you may be thinking that, gee, that sounds like a CRC if you're in the storage world, and there is some similarity. Checksums are typically, which are what CRCs produce, are primarily for error checking, which is a form of, if you will, integrity checking. Hashes are there to do, they produce message digest, and they really are focused on data integrity for the entire object or file, where CRC may be focused more on a block-by-block nature. So, but CRCs have the nice characteristic of being fairly fast and allows, for example, storage systems and networking technology to be able to adapt quickly to a detected error. All right, it's important to realize that this kind of activity doesn't give you any guarantees as to the source. Where did this come from? Do I really trust that the file that I've received is from Billy Bob Joe? And so you have to do a little more to do that. So the next one is message authentication, and this is where you actually get a determination as to just did the person who sent me this, is it really who I thought it was? And so using message authentication code algorithm, and effectively you're using a secret key that both parties, the transmitter, if you will, and the receiver both know, and that gets combined with essentially the input data, such that you have the ability on the other end to essentially repeat the process. And since only the two of you know that key and it's part of the input, if you're able to produce the same message digest, then you know that at least the file or object that you received came from somebody who knew that shared secret. Now, if you've shared it with a half a dozen people, then it'd be one of that half a dozen, but it would be a limited set. Now, this technique doesn't give you non-repudiation. In other words, the person who supposedly transmitted it could claim that, no, you created that, and I didn't do that. And that may be important for certain legal reasons, or, for example, if you're dealing with a will or something like that. Okay, so here's a pictorial version of what's going on. Sometimes this is a little easier to kind of understand, but you see in this particular case, you see the keys being injected in addition to having the arbitrary length input, kind of like the regular hash that we were talking about, and then how this whole process works. All right, so the next piece is the one that gets kind of fun. This is where basically digital signatures, and I'm going to go to the pictorial version of this. So here is an instance where you need to actually have an assurance that the message that you're receiving came from a particular sender. And you want that so that they can't say, I didn't do that. And so this is typically done using some form of digital signatures and using public key primitives or for message authentication. And you're essentially binding a signature to the message. So you're using if you remember John's discussion about asymmetric encryption, well, there's kind of a similar thing going here in that you're using a public and private keys, and these are basically being used where, for example, the signer's private key is being used to as part of this injection into a signature algorithm. But more importantly, you see that there's a message inputted to a hash function, produces a hash value. The signer's private key is basically used to encrypt, if you will, that hash value. The original message is transmitted, the signature is transmitted, and the process is reversed on the other side. The twist is that the signer's public key is basically used to extract the hash value that was basically signed, and then there's a calculation done on the verifier side of calculating their own hash value, and those two are compared, and if they match, then in that instance you get integrity, and you've also verified that the individual who you expected it to be from did in fact send it, and in fact that person would have a lot of difficulty basically saying, no, I did not do that, because they're the only ones that are supposed to have access to the private key, and that's really the value here. It turns out that this approach, the message is basically in the clear though, and so there is a process that you can use where if you want to also encrypt the message, then there's a recommended process, and essentially it's encrypt then sign approach is how they do it, and basically the part of the message that's before it goes into the hashing function, you're encrypting there so that the signature is on the encrypted component. And with that, I will stop and turn it over to Olga.
Thank you, Eric. Thank you very much. And let's talk about blockchain. So one thing which I would like to start with is saying that everything which was described by John and Eric previously is highly adaptable and implemented in a blockchain. And blockchain is just one technology which uses encryption and hashing and a lot of other data security algorithms to build protocols where you are removing the human, I would say, human trust aspect. So what is the blockchain? And as Eric mentioned, and John before, we have in a blockchain is basically segments of blocks. And in that block, you have three components: data, hash, and hash of the previous blocks. And if you remember the beginning of Eric's presentation, he said that in order to modify the block, you have to modify the hash. And that's a quite complicated process, especially if you are going to the blockchain. Overall, what is a blockchain? A blockchain is a distributed database which keeps a continuously growing list of records and protects them from the revision and tampering. That's going back and tying it to the Eric state of point that every block is marked with hash. And it's also a public ledger, because blockchain is one of the technologies in a distributed public ledger, and allows you to evaluate the basic statistics of the system. crypto mining, there is a big misunderstanding. Crypto mining, it was one of the first easiest implementations in the blockchain, but the technology needs to be abstracted from the cryptocurrency overall, and it can be used in a different types of aspects of our life. So how does the blockchain works? Each transaction is stored in a blockchain ledger, and then these blocks are broadcasted. So if I take the example, for example, of Amazon, right, and we have three main components. You have a private key cryptography, distributed networks, and a shared ledger, and accounting of the transactions. So transaction occurred, I send the request, I broadcast my public aspect of the transaction, which at the transaction level occurred, and it's getting an encryption of the private key. I broadcast it to public, and then you have a so-called network of computes, and they move your transaction over nodes. Nodes are each of the computer segments is a part of a network. You can call it a node. And then once transaction has a hash, has a public key, it gets moved over through the nodes. And if the transaction doesn't have any collisions, it gets approved, and the receiver on the receiving side, it gets added to the blockchain. So one more time, we have a transaction request, and we verify that transaction occurred. Each transaction has a certain information signature. Once transaction is verified, it gets put into the network node of computers. It's stored as a block. Once it's stored as a block, it has given a cache. And after that, it gets moved into the blockchain. And that blockchain will start building the ledger records. Now, that's on a blockchain. So there are certain limitations when it comes to data processing. For the blockchain technology. As Eric and John mentioned, when you are manipulating secure data with the hash assigned, you are experiencing a network delays. So one of the key elements which today technology is trying to address when it comes to blockchain are signature verification, redundancy, attaining consensus, complexity, and energy and resource consumption. Why is that? Because when we add each block to the so-called blockchain and put it on a node, we not only store the data of that node, but we have to store all the previous node data as well, and validate and verify and compare. And if a transaction is not getting approved, then you have to restart the process. That leads me into the today's topic, which is storage block-based technologies and protocols which exist today. So imagine that in 2015 and 2014, 2015, there were there were several protocols published by the Kolmogorov, Jembrovsky, and a couple of others. And one of them was stating it's a proof of space and proof of capacity. So to rehash what has been told previously, proof of capacity uses outputs of the Shabal 256 cryptography. And just like Eric mentioned, there are several implementations in cryptography, and Shabal 256 with the SHA technology are the most popular when it comes to proof of capacity algorithms. Shabal 256 is viewed as an ASIC resistant because it uses a memory back-to-back memory write when it's doing a so-called hard drive plotting. I have to take a step back and mention one thing. Proof of capacity is entire basis is stated that the protocol is using not the compute CPU power like in proof of work or networking resources, but storage device driver resources. So that means your highly powerful or unused storage devices can create a blockchain and allow you to transfer data using a proof of capacity protocol. One good thing about and positive about that is that when you are using a proof of capacity, you plot or create hashes on your hard drive only once. That's why Shabal 256 and the I/O memory writes are so relevant in this case. One example which I can give to you is out of practice. We had a flash memory summit last year, and I built a miner, and we had an NVMe device. It was OpenFlux system from Western Digital using NVM over Fabrics and NVMe. So in order for me to plot 7 terabyte drive, NVMe drive, it took me only 4 hours. If I do the same memory back-to-back writes on a regular SSD, it can take up to 23 days. So it's a quite efficient process when it comes to overall plotting the device. And then once you finish plotting, you no longer need to do any more additional memory writes because each hash is assigned to the memory block on a drive. And at that point, you start using memory reads by understanding the height and the depth of the block. And those blocks are predefined. What else can I tell you? When we are plotting the device, normally there is a technology called nonsense, but I will get to that in the next slide. Another positive thing on when we're building a proof of capacity, it's energy, green energy. And as you can see in the next slide, proof of space allows you to, in terms of energy consumption, this is example from Burstcoin versus Bitcoin, where if I'm using a CPUs and GPUs, it's 10 kilowatt. When I'm using a pure soft hard drives or NVMe drives, it drops down tremendously. So not only it's efficient method of transferring data by using existing storage devices, but it's also efficient in terms of energy consumption. A couple of the things which we need to mention. Proof of space and proof of capacity very frequently used interchangeably. And what it allows you to do, it allows you to use the memory space to complete the transactions. When it comes to the plotting or some other things, there is a different terminologies and exceptions, terminologies and commonly accepted statements made, such as deadline, block reward, base targets, network difficulty, and network difficulty is important. Block height is critical, especially when you're building a large size block. And then let's get back to what is the proof of space or proof of capacity. Like I mentioned before, the idea came out of the white paper by Krzysztof Petrak and Kolmogorov, and it was based on a basic aspects of how of the what I would call it, if anyone likes playing Japanese game called Go, it's a pebbles to hard memory or hard to pebbles. So hard memory hard functions to pebbles. That's what it is. And the way it would work is when you take it from the abstract view, you have ability to get the protocol communication between prover and verifier and have two distinct phases between them. One phase is initialization. The second one, once you finish the initialization between prover and verifier and you handshake it, you are going into the labeling. So you create a label pebble diagram. And once you are done, then you are, once it's verified, initialized, you complete the transaction. So what is the difference between proof of space and the contracts to the proof of work? One contributes only communication by the processors. The other one uses only the devices, memory storage devices. That's one of the important things. Another thing is important is if you are creating a large number of the hard-to-pebble graphs, you need to create you can create a so-called graph labeling problem. And that problem can be addressed, and just like it was done in the proof of space protocol, by the memory hardness function. Memory hardness function is used in proof of work very widely. Pebbling is also, but hardness to pebbling is unique to proof of space overall. Now, how does the proof of capacity work? The first thing which you do, like I mentioned, you have to plot your hard drive, and that builds a so-called hashes with nonsense. So when if I take that and apply our Shabal 256 technology, I build my 8-byte block heights, and I create the seed for each. Once the seeds are defined, I start processing the data and move it onto blockchain. So first I plot and I create with scoop 1, scoop 2, scoop 3, scoop 3, scoop 4. That will allow me to mark all my hashes on my drive, and I mark it clearly. Once I do that, I start pulling the blocks by the height and by the byte ID and account ID number. Then I apply the encryption, and once the encryption is applied, I put it on a chain, and then I create a hash to process the data. And the good thing about the plotting in a proof of space, like I mentioned previously, you can do it way in advance. So your turnaround time when you already are pulling blocks into the chain by nonsense are very non-relevant anymore. So now to come closer to the conclusion and talk about the role of cryptography in a blockchain. Cryptography can be described as a way to protect a certain information by keeping it private and confidential. It also allows you to keep information intact and original. It allows you to maintain the anonymity because, like we all know, the blockchain, one of the key aspects of the blockchain is the trustless protocols. And it also allows you to keep the unique authentication for all users. This is a block diagram of our SNIA proposed blockchain interoperability architecture, and the underlying reason for this, and this would be my call to action, at SNIA organization, we would like to create a communication protocol across multiple blockchains and multiple implementations of the blockchains in current existing environment and going forward environment. So my call to action is please join our blockchain group. It's just recently been formed, and your expertise and participation would be highly appreciated. And that will conclude my part. It's back to
Thank you, Olga.
you guys.
Thank you very much, and thanks to our audience. We've had a number of questions, and I think one of them, we're going to have to revert to the blog. I think the blog is going to be a useful way for us to answer some of these. And there's one in particular I just want to call out. I lost track on the explanation about proofs in blockchain. I'm afraid I didn't get it. What are these algorithms usable for? Blockchain is actually very novel at the moment, really new. And there are a huge number of concepts that we've introduced today in this presentation. Some of them old, some of them well understood, and some of them pretty new and novel. And I think what we need to do is take a bit of time in the blog to answer some in-depth. I've got several questions myself about how we use these technologies to ensure that our data is secure, to ensure that data, when it's moved about, doesn't get tampered with. So we'll do that. If you look at the attachments, you'll find one of the attachments was the blog, the blockchain storage blog, and we'll put up the answers and some more explanatory material about all this on that blog. In the meanwhile, you'll find there are more SNIA resources marked here in terms of our educational library and what we've done recently, and some upcoming presentations that we're going to be doing shortly over the next couple of months. The webcast itself is available in PDF format, and what I would like you to do is send us any more questions you may have. You can use the Twitter handle for that, or you can actually use the blog to ask questions, and we'll answer them there. And secondly, I'd like you on the way out of this presentation to rate the presentation. Remember, I asked you to rate this from 1 to 5 so that we get an understanding of what it is that we're doing well and what we're going to improve on. And if you have any commentary to make, please do so in the comment section for the ratings. In the meanwhile, I'd like to thank you all, my presenters today. I would like to thank you, the audience, for coming along to this webcast. And I hope that you have a good and enjoyable rest of your week. Thank you very much indeed for attending today.
Thank you, Alex.